Morning, everyone. Had some issues setting that up today. I'm not sure what was going on. How are we doing? Yeah, Maud, we can say that. Grades for 141 should come out today. Yishen, well, yeah, Maud, that's right. I'm not sure where you're going with that, though. Because it's ln n to the power ln n, and you're using ln n has e to the ln n, which is fine. Oh, I see what you're saying. Yeah. We are finishing chapter 11 today. I mean, you cannot let u be ln n, because then you would take u to be natural numbers, and ln n is not going to be a natural number. I don't know that I want to post a mock midterm. I was going to talk about the midterm. I don't know what the midterm will include yet, but certainly everything we've done so far and today. We'll probably end the material on Wednesday. I'll make an announcement in any case. Secondly, how do you prepare? Just make sure you're comfortable with the material. And in order to be comfortable with the material, you've got to do lots and lots and lots of exercises from the book. So tackle it as if it was the usual, a usual exam, usual sit-down exam, and you would prepare for that by doing lots of exercises from the book. You need to do the same thing. You're going to have 4 web works in total. The first one is already up. For the midterm, again, I mean, it's going to be a 72-hour midterm. It's really just a 2 or 3 hour exam, but you'll have 72 hours. You can use the internet, you can use Wolfram Alpha, and so on. However, the work that you submit needs to be your own. So when I say you can use Wolfram Alpha, you can use it to kind of test your answer. is it consistent with answers from Wolfram Alpha? But I certainly don't want you to use Wolfram Alpha to compute things and then say, well, that's the answer. No. So I want you to do the work, and I don't want you to use these websites where you can ask the question and somebody gives you the answer. That's cheating. I don't want to name those websites. You know what they are. And some people have done that for 141. And I mean, look, so some of the instructors are reporting them. So, no, you don't have to type anything. In fact, I don't want you to type anything. Write it in your own hand, take a picture, and upload it to CrowdMark. We're going to go through CrowdMark for the midterm and final. So that's what it is. You can assume the results we showed in class. P-series, you don't have to prove it again. Just refer to the P-series test, and you're good to go. Somebody's asking for the series 1 minus cosine 1 over n. I still haven't answered the series ln n, 1 over ln n to the power ln n. Let me think about that. I don't have a good answer for that yet. The midterm will be doable in 2 or 3 hours, exactly like the 141 final. I mean, some of you may have heard horror stories about the 141 final. Don't believe it. The 141 final was very doable. Look, it took me 90 minutes to do everything in complete detail, along with a marking scheme. I don't know anything about the exam. I haven't written it yet. I will make an announcement as soon as it's done. We will do more Maclaurin series today, so let's not worry too much about that right now. Quinn is asking, the book has known and important power series representations. I don't expect you to know any of these by heart. Rather, I expect you to be able to work them out in under a minute. Blue Pill is asking if there's a general way of figuring out a closed form for Maclaurin coefficients. There is not. Let's see what Ahmad is suggesting. Ahmad is suggesting that e to the ln n is n, so that ln n can be rewritten as ln of e to the ln n. Yeah, no, I think there's somewhat of an issue there. I don't. How are you getting the n to the ln of ln n being the same thing as the other one? I have to question that. I don't see it. I don't see it quite yet. So Yushin is asking for the question on the board, can we use a divergence test? Of course, you can always use it. And as n goes to infinity, 1 over n goes to 0. Cosine of 0 is 1. 1 minus 1 is 0. So ln n is equal to e to the ln of ln n. Is that right? I don't know. I don't think that's right. Can you prove that? Oh yeah, of course. Very nice. Yeah, the exponential and logarithms are inverse functions of each other, so this is just ln n. All right, very nice. So there it is. So 1 over ln n to the ln n is the same as 1 over e to the ln of ln n, the whole thing to the ln n, which is 1 over e to the ln n, ln of ln n. Which is 1 over e to the ln n, the whole thing to the ln of ln n, which is 1 over n to the ln of ln n. Oh, very nice. Very nice. Well done. Well done. And now for large n, this is going to be bigger than 1, and you're good to go. So this is going to be less than 1 over, let's say, n squared for n large enough. I mean, you still need to prove that, but there it is. Well done. Nicely done. Very well done. And let's look at this. We applied the divergence test. We concluded that this goes to 0. And so that doesn't help. We always have more it's always easier if you're dealing with sines than cosines, because you know how sine behaves. Cosine, why don't we multiply this by 1? For large values of n, this is close to 0. Cosine of 0 is 1, so the denominator is not going to be 0. We don't have an issue here. Right, well, I mean, limit comparison is what we're going to end up using, probably, but it's not clear what to compare to at this point in time. So let's multiply by 1 and see what happens. And this is 1 minus cos squared. And notice that the denominator is getting closer and closer to 2. So the denominator doesn't play a role here. And 1 minus cos squared is sine squared. And you know that sine of x, for x close to 0, behaves like x. So sine squared is going to behave like x squared. In other words, we're going to do a limit comparison with the series 1 over n squared, which you know converges. This is a convergent p series where p is equal to 2 bigger than 1. right? I mean, it wouldn't have been clear to do a limit comparison with 1 over n squared right from the beginning. At least it wouldn't have been clear to me. But now, by doing this, now it's clear. So let's do a limit comparison. And let's rewrite this, if you will, as 1 over 1 plus cos 1 over n times sine squared over 1 over n squared. Right? Why am I splitting it up this way? Well, as n goes to infinity, this just goes to 1/2. This limit exists, and it's not an issue. It's this limit which has the form 0 over 0. So we're going to evaluate this limit separately. So this has the form 0 over 0. If we apply L'Hopital's rule, derivative of sine is cos. Oops. So 2 sine 1 over n, cos 1 over n, times the derivative of the inside, which is negative 1 over n squared. And the derivative of the denominator is negative 2 over n cubed. The negatives cancel. The 1 over n squared cancels with this one. Let's rewrite everything properly. The 2's cancel out as well. Let's cancel those. So we're left with sine 1 over n, cosine 1 over n, over 1 over n. And again, this limit will be 1, right? That's what led us to do a limit comparison with 1 over n squared in the beginning anyways. Sine squared of 1 over n is not the same as sine of 1 over n squared. They are different. But sine x over x, as x goes to infinity, is 1. It actually is not. It's the limit as x goes to 0, which is 1. Right? And here, as n goes to infinity, this goes to 0. But, I mean, don't take my word for it. Again, as n goes to infinity, this goes to 0. Cosine of 0 is 1, so you can split that up. And if you just evaluate this thing, which has the form, right? So this goes to 1, and this has the form 0 over 0. And if you do a quick L'Hopital's rule to that, derivative of sine is cos, times the derivative of the inside. Derivative of the denominator is negative 1 over n squared. These cancel out. As n goes to infinity, this goes to 0. Cosine of 0 is 1. So this thing goes to 1. That goes to 1. So this whole limit is 1. And so this goes to 1. This goes to 1/2. So this whole limit is 1/2. 1/2 is bigger than 0, but less than infinity. So both series converge, or both series diverge. The 1 over n squared converges, so our series converges. by the limit comparison test. How are we doing? Questions? Well, we evaluated this limit separately because this limit goes to 1/2. This limit we just found to be 1. So we have this limit times this limit. This limit is 1. That's what we just worked out. This limit is 1/2. So the whole thing is 1/2. Look, we were working out just part of the limit. One quick question. Amar is asking, how can we write this as a fraction of integers? Well, this is 1.234 plus 567 over 1, 2, 3, 4, 5, 6 zeros plus 567 over 1, 2, 3, 4, 5, 6, 7, 8, 9 zeros and so on, right? 5, 6, 7 over 3 more zeros. So 1.234 is 1234 over 1,000. And this is 567 over 1,000 squared. 567 over 1,000 cubed. 567 over 1,000 to the 4, and so on and so on. And what you have here is a geometric series if you factor out the 567. Can you finish it up from there? Avery's asking why we choose to do it in groups of 5, 6, 7. Well, I mean, that's what the question was, right? It's a 5, 6, 7 that is repeating. So we have no choice. We have to go with what the question is asking. And here it's telling us that the 5, 6, 7 is repeating. Carl is asking why we chose to compare with 1 over n squared. After rewriting our series, we had sine squared of 1 over n over 1 plus cosine 1 over n. And if you recall, the limit as x goes to 0 of sine x over x is 1. So when x is very small, this limit is 1. Here, 1 over n is going to be the x. So sine 1 over n behaves like 1 over n. But we have sine squared, so if you square both sides, there it is. Do we want to finish that up just for completeness? 1234. I'm sure you worked it out already. This is going to be 567, 1 over 1,000 squared, over 1 minus 1 over 1,000 squared. Nope, over 1 minus 1 over 1,000. So there it is. 1234 over 1,000. 567 over 999 times 1,000. So this is 1234 times 999 plus 567 over 999,000. It's nice to whip out your calculator and calculate this. You'll see that that's exactly what you get. So that's what I mean by using Wolfram Alpha to check, right? All of this is your work on a midterm, let's say. And then your final answer, you check. Again, posting questions on those websites where you get other people to answer for you, that is no good. Moving on, questions? We were looking at Maclaurin series last time. We did a few. Maclaurin series for, exactly. Maclaurin series for the exponential function e to the x. We did the Maclaurin series for sine x. Why don't we take a moment to remind ourselves and look at the Maclaurin series for cosine x. As you know, I like to have two columns, the function and the function at 0. Cosine of 0 in this case is 1. Take the derivative. Derivative of cos is negative sine. Derivative at 0 is 0. Second derivative is negative cos. Second derivative at 0 is negative 1. And you keep going until you see a pattern arising. Derivative of negative cos is sine. Derivative of sine is cos. And of course, you have recognized, as was the case with the sine, that we are now back where we started. So the next 4 derivatives are just going to be a cycle of these. And so you see what the pattern is now. Abe is asking, can we form a Maclaurin series if we don't have a pattern emerging? The answer is yes. We'll see an example of that momentarily. First, let's work out the Maclaurin series for cosine x. As you know, f of x is f of 0 plus f prime of 0 over 1 factorial x. Second derivative at 0 over 2 factorial x squared, and so on and so on. Quinn is asking, if we see that a pattern starts at the third term, for example, can we just put the first 2 terms out of the sigma sign? Absolutely. And that does happen in practice. Sometimes a pattern only starts later on, and that's fine. You're going to write out the first few terms separately, and then just start your series wherever the pattern begins. There it is. So in this case, cosine x, sorry, cos x is f of 0, which is 1, plus the derivative at 0 over 1 factorial x, second derivative over 2 factorial x squared, third derivative over 3 factorial x cubed, fourth derivative over 4 factorial x to the 4, and so on and so on. Let's rewrite everything. Simplifying this as much as possible, getting rid of the zeros. This is 1 minus 1 over 2 factorial x squared, plus 1 over 4 factorial x to the 4. The next term would be, you know it's cycling through, negative 1 over 6 factorial x to the 6, plus 1 over 8 factorial x to the 8, and so on and so on. Can we describe this in a nice closed sigma notation form? We can. What do we notice? It's alternating. So negative 1 to the n. If I'm starting at 0, the first term is going to be positive and then negative and so on. Looking good. What else? The powers are all even. So you know how to describe an even number, x to the 2n, and the denominator, very much in the case of sine, the denominator is just the factorial of the power. So if the power is 2n, then this is 2n factorial. Abe is asking, can you remind us why fx is equal to the sum We'll do that in a moment. In fact, we're going to generalize this idea momentarily. So let's postpone that and we'll do it in general in a moment. But there it is. And you know, I mean, it's a good idea to write out the first few terms just to make sure that you haven't made any mistakes. When n is 0, this is -1 to the 0, which is 1. X to the 0, which is 1. And 0 factorial, which is 1 again. So you see this 0 factorial being important here. When n is 1, this is negative x squared over 2 factorial. So minus x squared over 2 factorial. Looking good, agreeing with what we had. When n is 2, -1 squared is 1. X to the 4 over 4 factorial. And so on and so on. Very nice. It's important to work out the interval of convergence. What is the interval of convergence? What values of x can you plug in here? Let's do the ratio test. Everywhere you see an n, you replace with n plus 1. The whole thing in absolute value, because you know the ratio test is only valid for positive terms. You're dividing by a fraction, let's multiply by the reciprocal. You're taking absolute values, let's get rid of these -1 business. This is x to the 2n plus 2, right? Be careful here. A lot of people want to make a mistake and say x to the 2n plus 1. That is not what's happening, right? You're replacing n with n plus 1. It's x to the 2n plus 2. Same with the denominator here. This is 2n plus 2 factorial. Flip this, 2n factorial over x to the 2n. X to the 2n's cancel, leaving you with an x squared on top. 2n factorial and 2n plus 2 factorial, you know how that cancels. Work it out. X squared over, you tell me. Anyone? X squared over 2n plus, well, the lag is too long. I know you know what it is. Thank you. 2n plus 1, 2n plus 2. And as n goes to infinity, denominator goes to infinity, numerator is x squared, so the whole limit is 0. 0 is less than 1, regardless of what x is. So the interval of convergence is all real numbers. Absolutely, thank you. Questions here? Let's do an example from the book. We are asked to find the Maclaurin series for this function. Cecilia is asking if we could estimate sine x with a series for cosine x by taking the derivative. An excellent question, which we'll answer in a moment. But a very nice question. I wanted to point something out, but I've erased it. Let me point out, I mean, I'm sure you still have the series for cosine x in front of you. Notice that cosine x is an even function, right? Because there's symmetry about the y-axis on the graph. And notice that in the power series representation, in the Maclaurin series, you just have the even powers of cosine. And same with the sine function, right? Sine is odd, and in the Maclaurin series, you just have the odd powers of x appearing. It's a nice observation there, which makes complete sense, right? Because the odd powers of x are themselves odd functions, whereas even powers of x are even functions. Let's take a moment to write out the Maclaurin series for ln of x plus 1. When x is 0. Yishen, a very nice observation there as well. And everybody talking about the derivative versus the integral. That's exactly where we're going with all of this. in about half an hour. Let's work out f of 0. And ln, when x is 0, you get ln of 1, which is 0. Take the derivative. Derivative of this is 1 over x plus 1. Derivative at 0 is 1. Second derivative, this is negative 1 over x plus 1 squared. Second derivative at 0 is negative 1. And you know, we continue until we see a pattern arising. Third derivative is 1 times 2 over x plus 1 cubed. Second derivative, third derivative at 0 rather, is 1 times 2. Fourth derivative, minus 1 times 2 times 3 over x plus 1 to the 4. Fourth derivative at 0, minus 1 times 2 times 3. Perhaps you're wondering why I'm not just writing this as negative 6, why I'm leaving it as 1 times 2 or 1 times 2 times 3. It's to see what the pattern is. When you simplify too much, you lose track of the power, right? But now, if you take the derivative again, you know that a 4 is going to come up, a negative 4. So the fifth derivative is going to be 1 times 2 times 3 times 4, and so on and so on. I think we see a pattern. If you don't, then you continue. You continue until you see a pattern. Now, some of you may be wondering, what if there is no pattern? How are you going to know that there isn't one? Well, the question is going to be different. The question is going to ask you for the first few non-zero terms. Because if there is no pattern, nobody's expecting you to come up with one. So here, let's recall our Maclaurin series formula. And so on and so on. In this case, ln of 1 plus x, f of 0 is 0. Derivative at 0 over 1 factorial. Second derivative over 2 factorial x squared. Third derivative. And then minus 1 times 2 times 3 over 4 factorial x to the 4. The next one would be 1 times 2 times 3 times 4 over 5 factorial x to the 5. Why don't we write down the next one just for fun? 1 times 2 times 3 times 4 times 5 over 6 factorial x squared, x to the 6, and so on, and so on. Clean that up. Now we simplify, and you see what happens, right? This is just x. This is minus 1/2 x squared. 1 times 2 over 3 factorial. 3 factorial is 1 times 2 times 3. So you're just left with a 3 in the denominator. And then the next term is negative. 1 times 2 times 3 divided by 1 times 2 times 3 times 4. There's just a 4 left. Next term, 1 over 5, x to the 5. You see what's happening? Minus 1 over 6, x to the 6, and so on and so on. Let's write that in a nice sigma notation. What does this look like? First of all, it's alternating, plus, minus, and so on. So let's throw in a -1 to the end. Maybe n plus 1, depending on how we work it out. Well, I mean, Yining is asking if we can just use n factorial over n plus 1 factorial. That's fine, but you should simplify that, right? N factorial over n plus 1 factorial is actually just n plus 1 in the bottom. Quinn is asking, would it be x to the n over n factorial? Well, notice that there's some simplification here, right? Not n factorial, but just exactly, right? X to whatever power, and then it's the denominator is the same thing. So it's x to the n over n. Where do we start? Well, we certainly don't want to start at 0 if we have an n there, so this better be 1. And if you start at 1, the first term is negative. So we can adjust -1 to the n plus 1. And now let's check. When n is 1, this is -1 squared, which is positive 1. X to the 1 over 1, so that's just x. Agreeing with our first term. Let's write out the second. When n is 2, this is -1 cubed, which is -1. X squared over 2. Very nice. And you can keep checking a few, but that'll be enough for us. You should do a few more, just to convince yourselves that there isn't a mistake. Cecil will, Cecile rather, not really sure, but short answer, yes. But we'll see that momentarily as well. All right, so there it is. There is your series representation. Here's your Maclaurin series for ln of 1 plus x. We have to ask the question, what is the interval of convergence? So let's work out what the interval of convergence is. So you know what to do. The whole thing in absolute value. Blah, blah, blah. Simplify that. This should be n plus 1. Anyways, I mean, these cancel out regardless. After suitable simplification, what do we have? We have absolute value of x n over n plus 1. Does everybody have that? Ahmad is asking, why do we say Taylor series representation and not approximation? We'll be able to answer that shortly, but the real answer is they're equal, right? This is equal to ln of 1 plus x. So it's not an approximation, it's actually equal. It's the same thing. As n goes to infinity, this is just a constant, so we can pull that out. And this has the form infinity over infinity. So whatever you want to do, a quick L'Hopital's rule gives you a limit of 1 over 1, which is 1. So the whole limit is absolute value of x. And we just apply the ratio test. So you know that this converges if x is less than 1. So we have convergence on this interval. Now we need to test the endpoints. If x is -1, we are looking at the series -1 to the n plus 1, -1 to the n over n, which is really the series -1 over n, or -1 over n. And what do you know about this series? Ahmad is asking, since the Taylor series is equal to the original, shouldn't both be defined on the same interval? Not necessarily. And the easy example is the geometric series. This is defined for all values except x equal to 1, whereas this only converges on -1 to 1. And here, as Tony suggested, this is a divergent p-series, where p is equal to 1, less than or equal to 1. So -1 is not included. What about +1? If x is 1, we're looking at the series -1 to the n plus 1, 1 over n. And you know this does not absolutely converge, right, by the same observation as over there, but there is hope for conditional. And this is an alternating series. Limit 1 over n is equal to 0, and the derivative is negative, so decreasing. And so the series converges by the alternating series test. So the interval of convergence does not include -1, but includes +1. Yining is asking why we don't test for conditional convergence for x equals -1, because we did not have an alternating series. Right? When x was -1, we had negative of the series 1 over n squared. Can you explain the last line again? This one here? Well, as Ahmad suggested, we're applying the alternating series test here. We have two conditions. we need the terms to go to 0 and to be decreasing. So that last part is the decreasing condition. How are we doing here? Questions? Right, we just found the Maclaurin series for the function ln of 1 plus x. Suppose the question had been, find the Maclaurin series for the function ln x. You see what the issue is, right? I mean, how do we find the Maclaurin series? We take our function, plug in 0. But already ln of 0 does not exist. So we're in trouble. And if you take the derivative of ln is 1 over x, and you're in trouble with the derivative at 0 as well. And so on for all the other derivatives. So that's problematic. Right? This function doesn't have a Maclaurin series. The question arises, can we generalize the idea of the Maclaurin series? Right? Moreover, this function, we found the interval of convergence to be -1 to 1. So we're not allowed to plug in x equal to 2 into your Maclaurin series. Right? 2 is outside of the interval of convergence. So what if we wanted to approximate ln of 3 using this technique? That would be out as well. Yushen is asking, can we just replace 1 plus x with x since we have this, but here, when x is 0, that's going to give you a 1 plus x, which is equal to 1, not 0. So we're still in trouble. That would essentially give you the same thing. Well, I mean, that's how we're going to generalize the idea. Right? We found a Maclaurin series where we were asking the question, can we write f of x as an infinite polynomial in this fashion? Right? As a power series like this, in powers of x. Very nice, everything worked out well if your function and its derivatives were all defined at 0. But what if it's not? Can we generalize this idea? Right, so these were Maclaurin series. Can we generalize, and instead of just powers of x, why not powers of x minus c? In the same way that we generalize power series. Can we have powers of x minus c instead? Where c is some fixed real number, usually known as the center. So c for center. That's going to be the center of our series. These were known as Maclaurin series. And its generalization is known as Taylor series. When c is 0, a Taylor series around 0 really is a Maclaurin series. So you see that it's an immediate generalization of Maclaurin series. Maclaurin series are a special case of Taylor series, where the center is 0. Let's go through the development again, thereby answering, I think, Carl, who asked the question, can we go through the development again? Let's do it in general for Taylor series. What must be the coefficients A0, A1, A2, and so on? The way we had worked that out in Maclaurin series is we had plugged in 0. When x is 0, all of these disappear and you're left with A0. Here, what do we want to plug in to make everything disappear? We're going to plug in the point C. If x is C, this is 0, this is 0, everything is 0 except A0. So A0 has to be f of C. Now we want the other terms. We want A1, A2, A3, and so on. What are you going to do? Same trick we did here, namely, differentiate. A0 is just a constant, so the derivative is gone. Derivative of x minus c is just 1. Derivative here, 2a2 x minus c. The next term, what is the derivative of the next term? You know what it is. Write it down. The next term, the derivative would be 3a3 x minus c squared, and so on. Plug in, thank you. Plug in x equal to c again to get rid of all the terms except the first one. When x is c, this is 0, everything is 0 except a1. So you see a1 is the derivative at c. Differentiate again. This is just a constant, so that's gone. Derivative here, 2a2. Derivative of x minus c is just 1. The other derivative, bring the 2 down. 2 times 3, a3 x minus c. And then you would have a 3 times 4, a4 x minus c squared. And so on and so on, and keep doing the usual. Plug in x equal to c. This is gone, this is gone. So you see that the second derivative at c is 2a2, or a2 is the second derivative over 2. And then you see what's going to happen, right? You're going to get a 3 factorial and then a 4 factorial and so on. You know, we already did it in the Maclaurin series. You kind of expect to see the same thing happening. What are we saying? An is going to be the nth derivative at c over n factorial. So that your function is f of c. Derivative at c over 1 factorial x minus c. Second derivative at c over 2 factorial x minus c squared. Third derivative at c over 3 factorial x minus c cubed. And so on and so on. So Taylor series, an immediate generalization of Maclaurin series. Let's take an example from the book. All right. Find the Taylor series for this function around a equals -3. So -3 is the center here. Tony's asking, what does a equal -3 mean? It means that that -3 is the center. Exactly that. So we're going to do exactly the same thing as we were doing. Does the center matter? What is the center going to affect? We'll see that, right? I mean, it's the same thing, right? That's your center here. So first of all, what does it affect? Your series is in terms of x minus the center instead of just powers of x. And then it also affects the coefficients. So we'll do exactly what we were doing from Maclaurin series, namely having those two columns, right? F of x, and we had f of 0, but of course that doesn't make sense here, and that's why the center is different. So when x is -3, this is -1/3, and you take the derivative. And the derivative at -3 is -1/3 squared. And you keep going until you see a pattern. So this is going to be 2 over x cubed. So the derivative, second derivative, is going to be -2 over 3 cubed. Again, right, you keep going until you see a pattern, until you can describe what the pattern is. -2 times 3 over x to the 4. So -2 times 3 over 3 to the 4. Do we see a pattern arising? Do we want to do one more? Fourth derivative, 2 times 3 times 4 over x to the 5. Fourth derivative at -3 is -2 times 3 times 4 over 3 to the 5, and so on and so on. I think we see a pattern, right? So f of x is f of c plus f prime of c over 1 factorial x minus c. Second derivative at c over 2 factorial x minus c squared, and so on and so on. Here, we're saying 1 over x. F of c is -1/3. Minus 1 over 3 squared over 1 factorial x minus c. X minus, well, here c is a, so this is going to be x plus 3. Second derivative, -2 over 3 cubed over 2 factorial x plus 3 squared minus 2 times 3 over 3 to the 4 over 3 factorial x plus 3 cubed. Fourth derivative, -2 times, well, minus 2 times 3 times 4 over 3 to the 5 over 4 factorial x plus 3 to the 4, and so on and so on. Have I made a mistake? Ahmad is suggesting n minus 1 over 3 to the n. Well, I mean, let's simplify. Right, the 2 and the 2 factorial cancel. 2 times 3 is 3 factorial, so this cancels. 2 times 2 times 4 is 4 factorial, so these all cancel. So let's rewrite this in a simpler form, minus 1 over 3 minus 1 over 3 squared x plus 3 minus 1 over 3 cubed x plus 3 squared 1 over 3 to the 4 x plus 3 to the 4, and so on and so on. I think we see the pattern. Let's describe that in a nice closed form. We can take a negative out of there. These are all powers of 3. So x plus 3 to the n, and these are powers of 3, which are 1 more than the power. So if it's x plus 3 to the n, it should be 3 to the n plus 1, where n starts at 0, because we want a constant first. Let's write out the first few terms just to make sure. When n is 0, this is 1 over 3. When n is 1, this is x plus 3 over 3 squared. When n is 2, x plus 3 squared over 3 cubed. Looking good. Looking very good. Ahmad is asking, oh, maybe not to me. Did Yishan ask a question earlier that I didn't see? Okay, perfect. There it is. There it is. We have this. And now, of course, the question, an associated question would be, what is the interval convergence? I have a mistake in the last term on the top line. Thank you. This should be Q. Thank you. There it is. Let's take a moment to figure out the interval convergence. And let's apply the ratio test for that. You know what to do. So negative x plus 3 to the n plus 1 over 3 to the n plus 2 divided by negative x plus 3 to the n over 3 to the n plus 1. The whole thing in absolute value. Blah, blah, blah there. After suitable simplification, you immediately see that this is x plus 3 over 3. Is that clear? 3 to the n plus 1 and 3 to the n plus 2 cancel, leaving you with just the 3. And same thing here. And you can forget the negatives because you're an absolute value. So that limit is x plus 3 over 3 in absolute value. And for convergence, you need this to be less than 1. So x plus 3 in absolute value should be less than 3. Or minus 3 less than x plus 3 less than 3. And if you subtract 3 from both sides, minus 6 less than x less than 0. This is your interval convergence. We need to test the endpoints. If x is 0, what are we looking at? If x is 0, this is 3 to the n over 3 to the n plus 1, which is the series 1 over 3. Conclusion? Conclusion here? Diverges by the divergence test. Limit of 1 over 3 is 1 over 3, which is non-zero. And if x is negative 6, what are we looking at? Negative 6 plus 3 is negative 3. So this is negative 3 to the n over 3 to the n plus 1, which is negative 1 to the n over 3. Conclusion? This limit does not exist, so series diverges by the divergence test again. Absolutely. So the interval convergence is negative 6 to 0, not including the endpoints. Questions here? How are we doing with the Taylor and Maclaurin series? Anyone? We're good? Here's a question that comes up naturally. Yishen is asking, if we take center at 5, will it give us a different Taylor series, but for the same function 1 over x? So the purpose of having a center is just a way to get around the 1 over 0. Exactly that. Exactly that, right? Here, your function 1 over x has this Taylor series, and it's valid for any point between negative 6 and 0. But you cannot plug in x equal to 5, right? If you wanted to approximate your function near 5, you would take a Taylor series around 5. And in that way, you could use it to maybe approximate your function. Questions? Well, here's a question that arises naturally. So the center is also useful to approximate functions. Well, that's the thing, right? I mean, here your function 1 over x, this is an easy function to deal with. You probably don't have to approximate anything. You plug in a value of x here, and you get your value. No worries there. However, if it's a function that's more complicated, and a few moments ago, we worked out the Maclaurin series for ln of 1 plus x. Now, this is not an easy function to deal with if you don't have a calculator. And imagine 100 years ago, or 200 years ago, when nobody had anything close to a calculator. How would you work with ln? What is ln of 2? That would have already been a difficult question to answer. But we worked out the Maclaurin series, and I think we had worked it out. What did we work it out to be? I want to say negative 1 to the n plus 1, x to the n over n. And we saw that positive 1 was in the interval of convergence. So ln of 2 is actually this thing. This is what ln of 2 is. And if you don't have a calculator, you can't do anything with that, but you can do something with this. If you add the first few terms, so that's 1 minus a half, plus 1/3 minus a quarter, and so on. You can add the first few terms, and that's going to give you an approximation. And since this is an alternating series, you know that the error is going to be less than the next term in line. So this will allow you to approximate ln 2 with as much accuracy as you want. How are we doing? But how are we sure the function is exactly equal to its Taylor series? And that's the excellent question that we're going to answer right now. Right, so Quinn is asking the good question, how do we know the function is exactly equal to its Taylor series? Or conversely, how do we know the Taylor series converges to the function itself? Is it always true that the function is equal to its Taylor series inside the interval of convergence? That's the question we want to tackle right now. And we're going to answer that question in a way that is familiar. And, you have the idea right here. We're going to split this up into the first few terms. right? So we can add the first few terms, let's say from 0 to k. And then what? Well, I mean, since it is an infinite sum, you're missing the rest. So you're missing the sum from k plus 1 to infinity. Right? I mean, the usual way, we've done this before, time and time again, when we're approximating sums. So it's the same thing, right? Because this is an infinite sum. So if you bring this to the other side, well, first of all, let me introduce some notation here. This is called the Taylor polynomial of degree k. Right? Because the largest power is k, and you'll have an x to the k in there. So it's a polynomial of degree k. And this, so by the way, this is denoted tk. And this is going to be called the remainder. Because it's what is left over. Usually denoted Rk. And you see what happens, right? If you bring this to the other side, f of x minus your Taylor polynomial is equal to the remainder. So if you take absolute value, the remainder is the error. It's how far your Taylor polynomial is, from the actual function. And in the same way that we had with sequence of partial sums or whatever, if this goes to 0, as k gets larger and larger, then your Taylor polynomial converges to f of x. So really the question is, when does the remainder go to 0? Right? All we need is the remainder to go to 0. If the remainder can be made very small, we're good to go. Let's talk a bit more about this remainder business. There's a beautiful theorem by Lagrange that gives you, so it's called the Lagrange remainder theorem. Which tells you what the remainder looks like. the remainder Rn, which you know to be the sum from n plus 1 onwards, actually is equal to the nth plus 1 derivative evaluated at some function at some point z for some z between x and c. As long as the function is continuously differentiable. N plus 1 times. For x in the interval of convergence. Right, so instead of having to deal with this infinite sum, it's actually equal to one term based on the nth plus 1 derivative. The proof of this makes use of the mean value theorem from Cal 1. I'm not going to discuss it, but there it is. In particular, let me point out that if the n plus 1 derivative is bounded, if the n plus 1 derivative is bounded for all x, then this is less than or equal to m, and as n goes to infinity, this can be replaced with m, and since this is in the interval of convergence, since x is in the interval of convergence, this whole thing is going to have to go to 0. What do we mean by bounded? We mean exactly this, that the nth plus 1 derivative is less than some constant m throughout the values of x. So not convergent to m, but less than or equal to m, let's say in the interval of convergence. We'll take an example. But all I'm suggesting here is that if the nth plus 1 derivative is less than m, then it forces the remainder to go to 0. and it forces the Taylor series to converge to the actual function. So in particular, if the derivatives are all bounded, you have convergence of the Taylor series. I mean, if you're answering a question like this on the midterm, you can refer to the theorem we studied in class. Let's take an example. Questions about the Lagrange remainder theorem before I erase it? So again, my point is, in particular, if all the derivatives are bounded, then your remainder has to go to 0, so the Taylor series has to converge to the original function. I think this is known as Taylor's inequality, yes. How do we prove they're all bounded? Well, I mean, you have to know some things about your function. So let's take an example. What happens if one of the terms where the nth derivative is 0? Nothing. Nothing wrong with that. Nothing wrong with that. The nth derivative being 0 is less than a constant. You're good to go. Approximate e to within 1/100, assuming that e is between 2 and 3. Abe, sorry, what was that? So the Taylor polynomial degree k is equal to, okay, well, the Taylor polynomial degree k is going to converge to the function only if the derivatives are bounded. It's not an if and only if statement, right? It's a sufficient condition. If the derivatives are all bounded, then yes. If the derivatives are all bounded, you're good to go. Let's take this example to illustrate. First of all, we're going to assume that e is between 2 and 3. This can be proven with relative ease. You don't need to know anything about e to prove that it's actually between 2 and 3, apart from a few things. Anyways, let's just take it for granted here, and let's approximate e to within 1/100. I mean, you know that e is 2.71 something something something. Who knows? But now let's see how we're going to do that. We're going to start with a function e to the x. We calculated last time the Maclaurin series, so we're not going to do it again. On an exam, though, I would expect you to take 1 minute of your time and work it out. I don't expect you to remember series by heart. Rather, I expect you to be able to work them out. But last time, we calculated the Maclaurin series to be x to the n over n factorial. And we saw the interval of convergence all real numbers, right? This converged to all real numbers. So if x is 1, we get that E is the series 1 over n factorial. And so on and so on. We are assuming here that the center is 0, right? Maclaurin series. We worked that out last time. This is one of the results from Thursday's class. But you see the issue. Do you see the issue? If you're trying to approximate this, this is not an alternating series. So we cannot say we're going to add some terms and it's less than or equal to the last term in line. That does not work here. Must all Taylor and Maclaurin series begin at 0? No. In fact, we did the Maclaurin series for ln of 1 plus x, and we made it start at 1. Right? So you see the issue here. We have to approximate this, but we don't have the luxury of the alternating series test. So what are we going to do? Well, luckily for us, we have the Taylor polynomial / remainder idea. Right? So if f of x is e to the x, if we go back to that Taylor and Maclaurin, to the Maclaurin series business, or Taylor series, which is just a generalization, or the difference between the function and the Taylor polynomial degree n is just the remainder Rn, and we saw the Lagrange remainder formula is the nth plus 1 derivative at some value z over n plus 1 factorial x minus c, or in this case x, because c is 0. Oh, let me write it. Where here c is 0, x is 1 because you want right? You want your f of x here is e to the x, and you want e, so x is 1. So in other words, e to the x, or e to the 1, minus tn of 1 is this. My question to you is, what is the nth plus 1 derivative? Well, look at your function. Your function is e to the x, and its derivative is e to the x, and so on. So the nth plus 1 derivative is just going to be e to the x. Nth plus 1 derivative at z is e to the z. We said x is 1, c is 0, so this is 1 to the n plus 1. Yishen is asking, can we use integral approximation to work this out? If we know how to integrate, certainly. But the problem is here, 1 over x factorial doesn't have an antiderivative. Right? In fact, x factorial isn't really even defined for values of x other than the natural numbers. You might be able to do something else. That's possible, as long as you justify, it would be acceptable. Well, I mean, here the function is e to the x, so its nth plus 1 derivative is just e to the x. Right? Chain rule doesn't play a role. No, but it's not, you're not differentiating e to the z, right? You're differentiating e to the x, and then you're plugging in z. For some z between c and x. Right, so that is your remainder term, and now z is between 0 and 1. I've rubbed it off, but we made the assumption that e is between 2 and 3. So e to the z is going to be at most 3 to the 1. So you see the difference between these two things is less than or equal to 3 over n plus 1 factorial. Yining is asking why z is between 0 and 1. That's what the Lagrange remainder theorem tells us. And in fact, you can see that this comes from immediately the mean value theorem. Right? Mean value theorem for some value between a and b. That's the 0 and 1 here. Can z be 0.5? It could. We don't know what it is. It's a theoretical result. We know that z exists between these two values. Somewhere, we don't know what it is. So as long as this is less than or equal to 1 over 100, you're good to go. So now, again, a little bit of trial and error here. If n is 5, what do we get? We get a 3 over 6 factorial. 1, 2, 3, 4, 5, 6. This is 24 times 30. So that is 1 over 24, 0. That's good. And if n is 4, you get 3 over 5 factorial. So I'm going to remove, I'm going to say that that's 1 over 48. Which is bigger than 1 over 100. So n equals 5 is what's important. This is the answer. So you're going to calculate T5, which is the sum from 0 to 5 of 1 over n factorial. So that is 1 plus 1 plus 1 over 2 factorial, 1 over 3 factorial, 1 over 4 factorial, 1 over 5 factorial. 1 over 40? Well, whatever. Have I made a mistake here then? 1224. So that's going to be 24 times 5. Thank you. Wait. 24 times 5. That's all right. Thank you. 1 over 40. The first is n equals to 6. Well, I mean, this n plus 1 is 6, but that corresponds to big N being 5. It's all good. And there it is. If you add these numbers up, these 1, 2, 3, 4, 5, 6 fractions, it's not a big deal to add that up. And that's going to approximate, right? So again, here's where you would use Wolfram alpha on an exam, right? I don't care about you plugging these into a calculator or an online calculator. Plug those in, get a value, a numerical decimal value, and whatever that number is, it's going to approximate E to within 1 over 100. So Yishen is asking, the goal here is to find how many terms we need to sum up using Taylor series to approximate to within 1 over 100. Exactly that. And this is where Taylor series are very useful. As I suggested last time, this is exactly what your calculator does to work out complicated functions. It approximates the values of those functions using Taylor series. How are we doing? And while I'm here, let me point out that in general, right, in the same way that we just did here, if your function is e to the x, it's n plus 1 derivative. Is e to the x. So So the n plus 1 derivative is going to be bounded in an interval. If you take any interval, for x in a bounded interval. Right, the n plus 1 derivative is always bounded in this case. So the Taylor series is going to converge to e to the x. Somebody's asking, do we plug into the remainder formula to calculate the error? Or was that already calculated as 1 over 240? That was already calculated, right? This was the actual error here. Well, less than or equal to the actual error. So everything was already calculated there in the 1 over 240. Right, so the Taylor series for e to the x is going to converge to e to the x. Similarly, for sines and cosines, right? The nth plus 1 derivative of sine and cos, I mean, there are really only 4 options. It's either going to be sine or cos, or negative sine or negative cos. But in any case, it's always less than or equal to 1. So it's bounded there again. Is x bounded by the interval of convergence? Certainly, you want x to be in the interval of convergence, but as you know here, the interval of convergence is all real values. So what you're going to do, you're going to bound, you're going to take an x in any interval. You're going to bound the interval, and therefore bound the derivative. And you can show that for any value of x, it has to converge to the function itself. The Taylor series has to converge to the function. And here, same idea here. Although here, sine is always bounded between -1 and 1. And same for cosine. So the Taylor series for sine and cos have to converge to the real thing, to the function itself. Quinn is asking, if you had ln of 1 plus x, well, if you take the derivative, you're already in the case of a 1 over 1 plus x. And the derivatives afterwards are even smaller, right? You get a 1 over 1 plus x squared, and so on and so on. So if x is large, well, I mean, you really all you want to do is stay away from -1. So if you bound your interval right, I mean, I think we had shown that the interval of convergence was -1 to 1 here. So if you bound your function, if you take any value of x in some closed and bounded interval away from -1, right? -1 is the issue. -1 makes this whole thing unbounded. But if you start with a fixed value of x, you can bound it away from -1, even if it's very close, right? Take the number. Take the example. Suppose x is -0.999. Very close to -1. But still not close enough that it becomes unbounded. This is going to be very large, but still bounded. So if you restrict your attention to the interval -0.9999, to 0, whatever, doesn't matter, then you can show that all the derivatives are going to be bounded on this interval. They're going to be very large, no doubt about that, but bounded nonetheless. So you can pick any bounded interval for x as long as it's in the interval of convergence, absolutely, as suggested by Tony. Right? Let's just look at the derivative here. This here, if you take any value in this interval, if z is in that interval, then z is bigger than or equal to negative 0.999. Or let's call it 9999 over 10,000. So if you add 1 to that, so 1 plus z is bigger than or equal to 1 plus this, which is 1 over 10,000. And if you cross multiply, 1 over 10,000, rather 10,000, 10,000 is bigger than or equal to 1 over 1 plus z. So you see that the derivative at z is less than or equal to 10,000. Very large, but still bounded in this interval. Amar is asking if the midterm starts or ends on the 15th. It's going to start. What are the cases where the derivatives are not bounded? The book has a very nice example of that. So really you're asking what kind of function has a Taylor series that doesn't converge to the function? And it's a beautiful question. Let me refer you to the book, but here is the function. It's a function which is 0 for values less than or equal to 0, and then it's e to the negative 1 over x. You can, I'll let you work out the Taylor series. First of all, it's not even clear that this function is continuous, first of all. It's not even clear that it's differentiable. So you have to answer all of these questions and then work out what the derivatives are at 0. So work out the Maclaurin series for this. So it's actually a very nice midterm type of question. Yeah. Something to think about. And see what happens. Will we have a short review on the 14th? If you've got questions on the 14th, I can answer. Otherwise, we'll do new material. If you want to approximate ln 3, where x has to be 0, then we have to change our center. Absolutely, right? I mean, if you want to approximate ln 3, you better have the value of x that gives you ln 3 in the interval of convergence. I think it's e to the, yeah, it's probably right. Thank you, Kun. Negative 1 over x squared. Yeah. All right, let's move on. Will we have enough time to finish the material? What material are we talking about? The Taylor series business? Yeah, we are cutting it kind of short. Well, let's hope so. Let's move on. So, I mean, what have we done? Given a function, we found a Taylor series representation or a power series representation for that function. Right? I mean, a Taylor series really is a power series representation. Ahmad is asking if we'll have enough time to finish all the 262 material. Well, whatever 262 material we do is going to be all the 262 material. So there's really no issue there. We'll have enough time. Power series representations for a given function are unique, right? I mean, we just show that if it converges, if the remainder goes to 0, the thing converges to the original function. My claim is that power series representations are unique. If you have a power series representation, then you have the power series representation. Where am I going with this? There are tricks to working out power series representations or Taylor and Maclaurin series in general, right? I mean, the usual way, function and its derivatives evaluated at those points, but the question arises naturally, are there other ways? In particular, I suggested that we saw that the idea that gave rise to all of this was the geometric series. And if you take this as the function and you work out its Maclaurin series, then I claim the Maclaurin series for this function will be exactly this. Now, this we got through a nice little trick, right? We saw a nice trick to conclude that this was equal to that, not through the Maclaurin series development. So the question arises, are there other such functions? Are there other tricks where we can get a Maclaurin series in a nice, quick way? And let's think about functions. You have a lot of experience with functions. You've been playing around with functions. What have you been doing, right? If you have two functions and you multiply them together, you get a new function. Now imagine these functions having a power representation, a power series representation themselves. If you multiply the two functions, you could equivalently multiply the two power series together. And that would result in a new power series, which is the product of the two functions that you started out with. If you have two functions and you multiply them together, you get a new function. If you have two functions and you divide them, you get a new function. You can divide power series and you get a new power series. You can add two functions and get a new function. You can add two power series and get a new power series. More importantly, think back to calculus 1 and 2. If you differentiate a function, you get a new function. You can differentiate power series term by term, and you'll get a new power series representation for the derivative. Same for the integral. Let's take a few examples of that. Well, in fact, let me state that as a theorem. And this will answer the question that we had originally. Why radius of convergence? Why are we bothering with that? I mean, that came up. Why not always talk about the interval of convergence? And so far, we had just talked about the interval of convergence as well. But here, in this theorem, the radius of convergence becomes important. Theorem, you can multiply, well, you can add, multiply, divide, compose, differentiate, and integrate. Term by term, a power series in its interval of convergence. In its interval of convergence. In this case, the radius of convergence of the new series is at least as large as what it was originally. Right? The radius of convergence is at least as large as the original. What does that mean? That means that the original could have had a finite interval of convergence, which may or may not include the endpoints, one or both, who knows? The new one, the radius is at least as large. So if the radius is the same, the endpoints may or may not be included here as well. And in the original, you could have had one endpoint which is not included in the original, and so on. The endpoints don't affect the actual radius. Yishen is asking, what if the two power series don't have the same interval? As long as there's overlap of the intervals, then the new series, if you were adding them together or multiplying them, the new series is going to converge on the intersection, at least on the intersection of the two. Exactly. How are we going to deal with the outside of the overlap? Of course you cannot. In general you cannot, but in particular, maybe something happens, who knows? What if one series starts at 2 and the other at 0? That is absolutely not an issue. Shall we modify them or have them start in the same value? You can do whatever you want. Let's take a few examples to illustrate all of these ideas. Right, notice here, let's not notice anything. Let's go back to an example we did. A few moments ago. Right, we looked at this and we worked out the Maclaurin series. We worked out the Maclaurin series in terms of powers of x plus 3 the long way, right? Function at -3, derivative at -3, and so on, until we saw a pattern arising. Now let's be smart. there's a nice trick. 1 over x, I'm going to add a 0. I'm adding a 0, so I'm not changing anything. Let me group the x plus 3, and let me factor out a negative 3 from the denominator. So I can rewrite it this way. And now, you recognize this as 1 over 1 minus a geometric series. So this is negative 1/3. This is the geometric series, x plus 3 over 3 to the n. And there it is. Exactly the result we had in 2 or 3 lines instead of several pages. We also looked at this question. Find the Maclaurin series for ln of 1 plus x. We did that, you and I together, the long way. Function at 0, derivative at 0, second derivative at 0, until we saw a pattern arising. But Yi Shen pointed out, if you take the derivative of ln of 1 plus x, is just 1 over x. 1 over 1 plus x. And if you rewrite this as 1 over 1 minus negative x, it now has the form 1 over 1 minus a. Geometric series again. This is minus x to the n. But that's the derivative. That's the derivative. That's not what you want. You don't want the derivative. You want the original function. How do you get back to the original function if you have the derivative? You know exactly what to do. Here we're saying this. But that's not what you want. You want ln, you're going to integrate. Find the antiderivative. And in the theorem I just erased, you can integrate term by term in the interval of convergence. This is just a constant. Antiderivative of x to the n is 1 over n plus 1, x to the n plus 1. plus some arbitrary constant of integration at the end. And antiderivative of this is ln of 1 plus x. X equals 0 is in the interval of convergence. So if you plug in x equal to 0, you get ln of 1 on the left. When x is 0, since this starts at 0, this is x and x squared and x cubed. All of these are powers of x that are bigger than or equal to 1. When x is 0, this whole thing is gone. So c has to be 0. In other words, ln of 1 plus x is this x to the n plus 1 over n plus 1. You could leave it as that. Let's make sure that it coincides with the answer we had before. If you make a change of variables, if k is n plus 1, then this is the sum from k equals 1 to infinity. This is negative 1 to the k minus 1. This is x to the k over k. I want to say we had a k plus 1 here. Convince yourselves that it doesn't make a difference. It's the same thing. When we are, Amar is asking, when we integrate it, isn't n a variable? It is not. N is treated as a constant, right? Because it's the x. We're integrating with respect to x here. Because we want ln of 1 plus x. So n does not depend on x. N is a constant with respect to x. Let's take a few examples from the book, right? Because these are all examples we had already seen. The c is applied to the entire sum. That's right. Yeah. Right, I mean, the c could have been on this side. You just need one constant of integration, so it doesn't have to be on both sides. Absolutely. At what time will the midterm open on Friday? I was thinking 2 p.m. How does that sound? You can discuss amongst yourselves. I was thinking 2 p.m. On Friday. We are asked to find the Maclaurin series for this function. And notice that, I mean, I've rubbed it off now, but we just saw that ln of 1 plus x was actually equal what did we see? Negative 1 to the n plus 1, x to the n over n. Right, I think we just worked that out. So now let's do a composition. So ln of 1 plus x squared, where you're replacing every value of x with x squared, is x squared to the n. Right? It's just a composition of functions. And that gives you x to the 2n over n. It is a power series representation for this, so it has to be the Maclaurin series. We said n equals 0, but I think we had an n plus 1 when n was 0, right? So if we make a change of variables to k, where k is n plus 1, then k is going to start at 1. So this is a power series representation for this, so it has to be the Maclaurin series. And then, right, so we have this part multiplied by x squared, both sides. So x squared, if you multiply both sides by x squared, there it is. How are we doing? Questions? We're already past our time, so perhaps we should end right here. We'll do maybe a few more examples next time. I was actually planning on finishing all of this already and doing some review of linear algebra. So here's what I'm going to suggest. I'm going to leave that up to you. I want you to review vectors if you feel the need to. So here's what I would like you to do. Review vectors. Dot and cross product. We're going to maybe just ever so slightly, quickly discuss those tomorrow, but I'm going to skip a lot of the, well, look, I mean, I assume everybody's done 133 here, so review these things. We'll talk about it quickly tomorrow and move on. Questions? Yushen, we substituted to k, that's right, yes. In answering the question, why does n not start at 0? Very good. Questions in the meantime? Anyone? So play around with this. These tricks, finding shortcuts to evaluating Taylor-Maclaurin series, very nice, so that you don't have to resort to that long way, although the long way always works. Ethan is asking if we have class on Victoria Day next Monday. We do not. Very good. So thank you for coming. I will see you tomorrow. Practice this and review vectors, dot, and cross product as well. It is. I'm missing an x squared here. Thank you. Absolutely. Estimate the series, correct to 5 decimal places, set the integration, or yeah. Well, I mean, look, Yushen is asking, how How can we know if 0.00001 doesn't work? Well, again, right? I mean, you need a starting point. And it could work in this case. I strongly suspect that 0.00001, you never actually get that, but rather something better, but you never know. They could both work. And I suspect that you would get the same answer. Absolutely. N bigger than or equal to 3. Yes. Right? I mean, again, you never know. You start with a starting point. It's usually half. Yes. So 0.5 to the next is better. Absolutely. It's safer in all cases. Yes. Yeah. Absolutely. Might still not be sufficient, as you know, but it's safer. Very good. So I'll see you tomorrow. Thank you all for coming. And I'll release the midterm at 2 p.m. on Friday. Questions? All right. I'll see you guys tomorrow. Lyra has a question, perhaps? I'll hold on a few moments if you do. You should work out the interval of convergence, right? I mean, you should work out the interval of convergence here. On an exam, this would be certainly a valid follow-up question. Of course, you don't have to do anything that I don't ask for, but you should expect on an exam that I will ask for the interval of convergence. Yushed is asking about 2 to the 1 over n minus 1. Can we do this by multiplying by 1 as in the cosine example? Tempting. 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 Did you get anywhere doing that? Why don't we try the ratio test? Is that going to be good? I don't expect the ratio test to be any good. Yeah. Lyra is asking to apply substitution. The interval of convergence must be related to the original. In other words, overlapping. Well, I mean, let's say this, no, but it will affect the interval of convergence. Carl, I think you mean that we cannot split these up individually, and that's correct. You cannot split them up because both of these would be divergent, but perhaps together you get convergence nonetheless. Let me do a limit comparison with the series 1 over n. I think that'll do it. Let's do a limit comparison with the series 1 over n, see what happens. And of course, the obvious question arises, where does this come from? Let's hold off on that and do a limit comparison, see what happens. And you'll understand exactly where it's coming from. Limit comparison where this is a divergent series, which is a divergent p series. P is equal to 1, less than or equal to 1. Right, if we look at this, as n goes to infinity, this goes to 0. 2 to the 0 is 1, 1 minus 1 is 0, and this is 0 as well. The derivative, so we can apply L'Hopital's rule, the derivative is 2 to the 1 over n ln 2 times the derivative of the inside. The derivative of the denominator. So you see that these two things cancel out, and that's why I chose this as the limit comparison, because I was thinking ahead, what is the derivative of this? And the derivative essentially behaves like 1 over n squared. What other function has the same derivative? Namely 1 over n. So these cancel out nicely, and now as n goes to infinity, this goes to 1, right? 1 over n goes to 0, 2 to the 0 is 1, so you get a ln 2. Ln 2 is between 0 and infinity. So both behave, both behave in the same way, both converge or both diverge. This one diverges, so that one diverges by the limit comparison test. Tricky, very tricky, but there it is. Tricky in the sense that you didn't really see what to do a limit comparison test with, but by taking the derivative, then it becomes clear. How are we doing here? Any other questions? If there's anything, you can always email me. Otherwise, I will see you tomorrow. Thank you all for coming. I'll post the stream on my courses momentarily.